Most buyers match solar panel power to inverter power. That's a fast start, but it's not enough. Good string design must also check voltage, temperature, MPPT range, and inverter limits. This in TH's video. I'll show you how I do that, and why 16 modules per string is the practical target in this 420-watt module and 80-kilowatt inverter example. A lot of people only compare panel watts and inverter kilowatts. That's fine as a starting point, but it should never be the final design method, because a solar module does not output rated power all day. In normal conditions, actual output may only be around 70% of rated power. Even in very good weather, it may only reach around 90%. So a system that looks perfectly matched on paper may still leave inverter capacity and used for much of the day. This is one of the most common mistakes I see in early project discussions. Buyers focus on total watts, but ignore operating voltage. And voltage is where real string design begins. Before I decide how many modules go into one string, I want to know 4 things. First, will the string stay below the inverter's maximum DC input voltage? Second, will the string stay inside the inverter's MPPT operating range? Third, will the system still be safe when local temperature drops in winter? And fourth, will the working voltage sit near a better efficiency zone for the inverter? So for me, good string design is not just a safety check. It's also a performance decision. Before I build a string, I always start with the module data sheet. The key values I look at are STC, VOC, VMP, ISC, IMP, and the voltage temperature coefficient. Let me explain that in a simpler way. STC is just the standard reference condition. It gives me a starting point for all calculations. VOC, or open circuit voltage, tells me the highest voltage risk. VMP, or peak power voltage, tells me where the module works around its best power point. ISC and IMP matter too, but when I'm deciding how many modules go in series, voltage is the first filter. And temperature is where many design mistakes begin, because the voltage temperature coefficient is negative. That means when temperature drops, VOC goes up. This is very important. Many people think cold weather only affects battery performance or energy production. But in solar string design, cold weather can push string voltage too high. That's why I never check voltage only at 25 degrees Celsius. I always recalculate VOC at the local minimum temperature. In this example, the 420-watt module has a VOC of 49.2 volts and a voltage temperature coefficient of minus 0.3%. When the ambient temperature drops to 0 degrees Celsius, the recalculated VOC rises to 52.89 volts. Once I understand the module side, I move to the inverter side. And this is where the real design window appears. I only accept a string design after it passes 3 checks. The first is the maximum DC input voltage. This is the hard safety limit. If the string VOC under cold conditions goes above that limit, the design is wrong. I don't care if the wattage looks attractive. I don't care if the total capacity looks close to the inverter size. If the voltage can cross the DC limit, I remove that option immediately. The second check is the MPPT operating voltage range. A string may still be below the DC maximum limit, but that does not automatically mean it is a good design. If the string working voltage does not sit inside the MPPT range, the inverter cannot track and use the array properly. The third check is even more practical. I want the actual working voltage to be close to the inverter's better operating zone, because 2 options may both be allowed, but one can still perform better in daily use. A simple rule of thumb is this. If the AC grid voltage is 230 volts, the inverter's rated operating voltage is often around 360 volts. If the AC grid voltage is 400 volts, it is often around 580 volts. And if the AC grid voltage is 480 volts, it is often around 700 volts. This kind of logic helps me move from a merely possible design to a stronger design. And I also keep one more rule in mind. If strings are connected to the same MPPT channel, they should have the same number of modules, the same orientation, and the same tilt angle. Ignoring that rule can reduce yield in real projects. Now let's look at the real case. The example uses a max 80 kTl 3LV inverter and 420-watt solar modules. The local extreme low temperature is minus 25 degrees Celsius. The extreme high temperature is 50 degrees Celsius. The inverter maximum DC input voltage is 1100 volts, and the MPPT voltage range is 200 to 1000 volts. First, I use the low temperature condition to control the maximum number of modules in one string. Because VOC rises when temperature drops, this is the condition that protects the inverter from overvoltage. The result is this. The maximum value of N must be less than or equal to 19.44. Next, I use the MPPT condition to define the acceptable working range. The result is 5.29 less than or equal to N and N less than or equal to 21.31. I still want the operating voltage to sit near a better efficiency point, so I use the midpoint of the MPPT range. The MPPT range is 200 to 1000 volts. The midpoint is 600 volts. Then I use the module peak power voltage, which is around 35 to 38 volts. If I use 37 volts as a practical reference, then 600 divided by 37 is about 16.22. That is why 16 modules per string becomes the practical target. So the method is very clear. First, find the safety limit. Second, find the MPPT window. Third, narrow it to the real integer range. And fourth, choose the point that places the string near a better operating voltage. That is how I move from guesswork to a design that is safer, clearer, and more useful in real projects. Welcome to reach out us for free solar power system proposal and best solar power system kits price from China factory. Website www.adiansolarstreetlight.com. WhatsApp +86 1586 714 1854.